Alright, this problem, 2011, for response number 1, was on your quiz, and I want to go over it and talk about it. Make sure that you have an idea of what you're doing when you do this. This talks about how a professional sports team evaluates their players. They base it off of two things. They base it off of speed, and they base it off of strength. Speed and strength are what they really are interested in. They start this problem by talking about speed being measured in terms of your 40 yards dash, basically. Smaller times means you're a faster runner than larger times. They also give you this information there. They tell you that the mean is 4.6 of this, standard deviation is 15 seconds, and the minimum value of this entire distribution. So the fastest time we're going to be talking about is 4.4 seconds. This is all I give you, and they tell you in the first part of A, using the empirical rule and based on the relationship between the mean, standard deviation, and minimum time, is it reasonable to believe that the distribution of 40-yard times is approximately normal? The key here is using the empirical rule. Let's set a curve up using the empirical rule. So we know that if this were a normal distribution, that's the problem here. We don't know if it's normal or not. They're just asking us to base the relationship of the mean, standard deviation, and minimum time. Well, if it is normal, we will look unimodal and roughly symmetric like this, right? So we set the mean at the center of this curve, which for this case is 4.6. And then within one standard deviation to the right, we're going to add 0.15, so that will be 4.75. Go out another standard deviation would be 4.9, and go out one more would be 5.05. Come back this way, you would have 4.45. Just subtracting 0.15 from 4.6, 4.30, and then 4.15. So remember, when we use the normal distribution of the empirical rule says that within one standard deviation lies 68% of the data. Within two standard deviations lies 95% of the data. And within three standard deviations, we should have 99.7% of the data. So when I look at this, here's what this is asking me. Using the mean and the standard deviation, which was what we did here to set the curve up, and now we need to involve the third thing, which is the minimum time. The minimum time is 4.4 seconds. Where does 4.4 seconds fall at on this curve? When we look at it, 4.4 seconds is going to fall somewhere right here. That means the absolute minimum time that somebody actually ran was 4.4 seconds, which is here. When you're looking at this curve now, the question is, could this data have came from a normal distribution? Well, if it came from a normal distribution, we'd expect to see times of at least 4.15 over here, and at most 5.05, right? But we're getting a time, our lowest time possible is 4.4. That's the lowest time possible. That's not even within that's not even two standard deviations out. So the question becomes, if this is the lowest time, and it's supposed to be modeled by this distribution here, could this data have came from a normal distribution? And in that case, the answer is no. And it's no because the minimum time of 4.4 seconds is not even negative 2 standard deviations away. We'd expect this distribution to have times of the ones modeled on on our normal curve. So we'd expect at least to get not very many, but a few times out here 4.15 seconds, and not very many, but a few out here 5.05 seconds. We're never going to get a time that is going to be less than 4.4 seconds. So that means this data couldn't have came from normal distribution, based off of the information that was given to us. Look at part B. Strength is measured by the amount of weight lifted, with more weight indicating more desirable or greater strength. From previous strength data for all players in the position, the amount of weight lifted has a mean of 310 pounds and a standard deviation of 25 pounds, shown in the table. Calculate and interpret the z-score for a player in this position who can lift a weight of 370 pounds. So this is basically your x. And remember, to find a z-score, z is equal to x minus mu divided by sigma. So here we have 370 minus 310 divided by 25. We get a z-score of 2.4. Well, what does that 2.4 tell us? Remember, a z-score tells you how many standard deviations you are above or below the mean. So with respect to this, if this were a normal curve or a normal distribution, the mean would be at 310, and here's the score of 370. That corresponds to, if we standardize this curve and make this mean 0, this number would be 2.4 standard deviations above that mean. So this is telling us that the person who can lift 370 pounds has a, or is, this individual can lift 2.4 standard deviations above the mean, or above the average amount. That doesn't mean that he's 2.4 times stronger than the average person. It just means that he's 2.4 standard deviations above what the average person normally lifts. The last part says, the characteristics of speed and strength are considered to be of equal importance to the team in selecting a player. Based on the information and about the mean standard deviations and the strength data for all players in the measurements listed in the table for players A and B, which players should the team select? And there I give you this hint, and I tell you that, in other words, which one is better with respect to their peers. When you see this, you should automatically think to yourself, find a z-score. So when we find the z-score, we're going to find the z-score of player A's 40-yard time, player B's 40-yard time. Player A's weight lifted, player B's weight lifted. So when we do this, we say player A's 40-yard dash. So we'll find z of player A 40-yard dash first, and that's equal to 4.42 seconds minus, well, the mean of this distribution right here, of the 40-yard dash distribution, was 60, or 4.6, over standard deviation, which is 0.15. We'll also find this 40-yard dash for player B. And that's going to be 4.57 minus 4.60 again, divided by 0.15. So calculating these z-scores, we get the first one for players A 40-yard dash time, 2 minus 0.15. That's equal to a negative 1.2. Calculating player B's 40-yard dash time. It's equal to negative 0.2. Now we need to do the exact same thing for their weightlifting. So we'll say that player A's weightlifting is his weight lifted was 370 minus the mean, which is 310 divided by 25. We calculated that earlier would be 2.4. And then the other one is player B's weight lifted is 375 minus 310 divided by 25. So that is going to be 375 minus 310 divided by 25, 2.6. So what do these numbers mean? When we look at them, they're z-scores. So z-scores tell us how far above the average we are, or how far below we are with respect to the average. These negatives mean we're going to fall below the average, which in terms of speed is a good thing. That means you're faster. If you look at this and you compare A and B, who is the faster runner? Well, clearly it's going to be A, because this z-score is way below the mean. Negative 1.2 standard deviations. He's only negative 0.2 standard deviations. So A is a much faster runner. Who is a more powerful weightlifter or stronger player? Well, this time you want larger z-scores because you're talking positive. 2.4 and 2.6, which means B is relatively stronger than A. But he isn't that much stronger. He's only 0.2 standard deviations stronger, right? So when we look at this, if you're basing it off of the two players you would like to take, clearly the advantage comes for A in speed. There's a slight advantage for B in weight. Since the clear advantage for A in speed is better, with respect to both categories, the best player is going to be A. And the reason A is the best player is because not only is he the faster player, but he's much faster than B. B's stronger, but A is much faster when you look at their z-scores. So A is much faster than B, and wow, we'll say wow, B is only marginally stronger. The second free response that we did on the quiz talked about a machine that was used to fill soda bottles and how consumers want a certain number, or when these companies publish their labels, they put those numbers on there so the consumers expect to get certain amounts. And it says the bottle label contains 2.0 liters, but extra room at the top of the bottle allows for a maximum of 2.5 liters. So the maximum amount a bottle can hold is 2.25 liters. The standard deviation of the amount of soda put into the bottles by the machine is known to be 0.5, and it follows a normal distribution. Alright? So this says, overfilling the bottles causes a mess on the assembly line, but consumers will complain if bottles contain less than 2 liters. So we don't want to give them less than 2 liters. That's what they're saying. If the machine is set to fill the bottles with an average of 2.08 liters, so this is the average. What proportion of bottles will be overfilled? Well, when are you going to be overfilled? That's the real question. We know that the maximum bottle can hold is 2.25 liters. So you're overfilled if you're anything greater than 2.25 liters. We know we have a mean of 2.08 on this curve now and a standard deviation of this right here. So that means for this first problem, x is approximately normal. They tell us it's the normal distribution with a mean of 2.08 and a standard deviation of 0.15. So calculating the z-score, or let's draw a curve first. Let's draw a curve. Where does the mean sit at? 2.08. We're looking at it to be overfilled. Overfill the curve when it's greater than 2.25 liters. So anything over is going to be overfilled. Remember the first step for any problem like this, calculate the z-score. So z is equal to x, which is 2.25 minus 2.08 mu divided by sigma, which is 0.15. I'm going to calculate this. That equals 1.133. So what I want to know is, when is the probability that X is going to be overfilled. So that's when X is greater than or equal to 2.25, it becomes overfilled. Or the z-score we just found is when the probability that z is greater than or equal to 1.133. And remember, this is just a normal probability, so you're going to calculate in your normal probability where, so second var, normal CDF. The lower bound of this distribution is right here at 2.25, or the z-score of 1.133. The upper bound is going to be a bunch of 9s. Press enter. You get 0.129%, or 0.129, which is, so about 12.9% are overfilled. Or 13% is what you want to call it. If management requires that no more than 3%, so look what they've done now. They've given me a percent, which means we associate this percent with an area, which tells me already I'm going to be using inverse norm. So if they require no more than 3% of the bottles should be overfilled, the machine should be set to fill the bottles with what mean? So now you're looking for a mean. And we're going backwards. We know what z-scores are equal to. Z is equal to x minus the mean divided by sigma. Well, I know I can find the z-score from the area. And to find it, I'm going to do inverse norm. And I want no more than 3% of the bottles to be overfilled. So if it's no more than 3%, working backwards, that's actually going to be, remember, the curve only calculates to the left. So no more than 3%, this would be the 3% out here. Inverse norm only calculates back here, though. So what percent is this going to be back here? That's 97%. So I'm going to do inverse norm of 0.97, and that's going to give me a z-score. And that z is equal to 1.881. So here's what I know. I know the z-score is 1.881. I know that it overfills at what x value? Well, 2.25 is when they tell me it overfills. I'm looking for the new mean amount that's going to keep it at that z-score. And I know sigma is 0.15, so plugging in what I know the z value is 1.881. That's equal to, what x value will keep me, or the x value I already know is that it's 2.25. That's the overfilling value. Minus what mean divided by the standard deviation is 0.15. Solving this equation for the mean. So we multiply both sides by 0.15 first. Times 1.881. 0.28215. 0.28215 is equal to 2.25 minus mu. Subtract out 2.25 from both sides. So minus 2.25. I get negative 1.967 equals mu, equals negative mu, which means that mu is equal to, divided by negative 1, mu is equal to 1.967. So if you set it to this, only 3% of your bottles will be overfilled. That's what this is saying. And the last part says, complaints from consumers about underfilled bottles lead the company to set the mean amount at 2.15 liters. So they've gotten complaints that people are underfilling bottles because they were worried about overfilling so much, so they set it at a higher mean. In this situation, what standard deviation would allow for no more than 3% of the bottles to be overfilled? Well, again, you still want 3% of the bottles to be overfilled, so we know that z-score already is 1.881. But this time they've changed it on us. They told us that the actual mean amount is. We know it still overflows at 2.25 liters, so we'll set up the z-score like this. 1.881. This is equal to, we know the z-score for overfilling is 2.25 minus the mean that they've given us now is 2.15. I need to find sigma, so I'm going backwards. Alright, so to Find sigma. Rearrange this equation for sigma. So when you rearrange for sigma, multiply both sides by sigma. And then you're going to divide by this 1.81, so you get this. Sigma is equal to 2.25 minus 2.15 divided by 1.881. Plug that into a calculator. Divided by, and I get sigma equal to 0.053. So this value right here, if you set the standard deviation to that, we get a standard deviation of 0.053. We can raise our mean, lower your standard deviation, and it's going to keep it at 3%.